Hi, this is Professor Cummings, and I wanted to talk to you about a problem, or work through another example problem. Again, still looking over gearing, and this is going to be a simple gear train. It's a 17-tooth spur pinion. The driver is known as the pinion, and has a diametral pitch of 8 teeth per inch, and runs at 1120 revolutions per minute. So that is the driver gear. And it drives a gear that is at a speed of 544 revolutions per minute. So it's going from 1120 for the driver and to 544 for the driven. Find the number of teeth on the gear, the driven gear, and the theoretical center. So this is what we're looking at, 17 teeth on the smaller gear, the driver, 8 teeth per inch, 1120 revolutions per minute, and 544 is the output, or on the driven gear. So let's put everything together, organize ourselves. So what do we have given? Again, the information for the driver, 17 teeth, the rotational speed, 1120, and the diametral pitch of 8 teeth per inch. And the driven, the only thing we know is the output speed, 544 revolutions per minute. And we're being asked to find the number of teeth on the driven gear and that center-to-center distance. And in order to do this, we're going to know, or want to know, the velocity ratio. In this case, you could calculate that several different ways, but we have enough information based on the fact that we have the input and the output speed. And we could have just as easily done that if we had the information, the diameter, if we had known the teeth before. There's several ways you can get this because there's several ratios. So long as the diametral pitch is the same, there's several things that start falling into line. That was a way to get that velocity ratio. So let's see. So we have this information, and we do know the equation for the velocity ratio. So let's go ahead and start with the number of teeth, using that, or find the number of teeth. And what we can do is we can take that velocity ratio, and because the diametral pitch is consistent, we know we can relate this to several other things with the gears. So we got an equation for the velocity ratio. The rotational speed in over the rotational speed out, which is also going to equal to the teeth on the output gear, the driven gear, over the teeth on the input gear. Again, because that diametral pitch stays the same. So if we just plug those into the equation, we can know that we've got 1120 over 544 for the rotational speed in versus out. It's going to equal to the ratio of the number of teeth on the output divided by the number of teeth on the input. So all we have to do is solve for the output teeth, or multiply both sides by 17 teeth. The revolutions per minute are going to cancel. And we're going to be left with the proper units on the output teeth, and that will be 35 teeth. So it's that simple, just a ratio between them. And you again remember, if you looked at our dynamics problems, those rotational problems, that this is consistent, that it is a rotation, the rotation ratio between the rotations of both gear. And you also know that these have a common tangential velocity between them. So that's the first thing we got. We got the number of teeth on the output gear. So that was one of the first things we needed to know. We also need to know that center-to-center distance. So we do have some information here. One is that diametral pitch. So we're going to have to be able to use that as well as the number of teeth to figure out how big these gears actually are. So we got that is, just finding the pitch circle diameters. That's what we're going to end up finding. And the equation for that, again, is fairly simple, fairly straightforward. We're going to divide the number of teeth by the diametral pitch. Again, for the input gear, that's 17 teeth divided by 8 teeth per inch. The teeth cancel. You end up with 2.125 inches, or 2 1/8 inch, as far as the diametral pitch. And remember, the diametral pitch only goes to that point. The pitch point, or the line of action on the gear. So it's not the actual gear itself. It's It's actually within the gear right on the 2 still. Now we can do the same. We do know the number of teeth on the output gear, and we do have its same diametral pitch. So it's just 35 teeth divided by 8 teeth per inch, and it's just twice the input gear, or 4.375 inches. And again, this is why you can actually use this type of information for the velocity ratio. It's just the same ratio between the teeth. So we've got the input and output rotational speed, the number of teeth, and the diameters can all come into that same ratio with the velocity ratio. Now, we still need to use this information for that center to center distance, which is a pretty straightforward equation. Or they call it the theoretical centers, which is the diameter of the input plus the diameter of the output divided by 2. So 2.125 plus 4.375 divided by 2. And that tells us that the distance from center to center is going to be 3 1/4, or 3.25 inches. So that wasn't a very long video, just real straightforward. Again, this is Professor Cummings. Go ahead and like the video. Please share the video to anybody who might need this information. And also subscribe if you haven't subscribed to the channel. And again, thanks for watching, and I will talk to you in the next video.